I want to talk about the famous Theorem of Pythagoras, which was established over 2,500 years ago. And it could easily be one of the most useful theorems in all of mathematics. Taylor's theorem is a strong contender for that as well. But I want to talk about this with a view to extending the theorem and posing some interesting problems. Now, the theorem goes like this. You need a right angle triangle. So this angle here has got to be 90 degrees. And if we label the length of the sides of this triangle, A, B, and C is the length of what is called the hypotenuse. The side opposite the right angle is the hypotenuse. And we're looking for a relationship between A, B, and C. Let's give ourselves a right angle triangle. And let's cunningly place copies of this triangle like this. Put one here, put one there, put one there. And you see a square is formed in the center. The length of the sides is C, C, C all around. Let's put in the other lengths, A, and then A over here, and A over here. And the B lengths are there, 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 and there. Now, the area of a triangle is half the length of the base times the height. And in this case, the area of this triangle is a half AB. Now, let's make this observation. The area of the square is, of course, C squared. And that area is the area of this whole large square minus 4 of these triangles, 4A. The area of the large square is A plus B, that length squared, minus 4 areas of the triangle. Let's just multiply this out. So it's A squared plus 2AB plus B squared minus 2AB. And the 2AB's disappear, and it's A squared plus B squared. So C squared is A squared plus B squared. The square on the hypotenuse is the sum of the squares on the other two sides. There is an immediate application of Pythagoras' theorem to Cartesian geometry. If that's our normal xy plane, and this is the origin at 0, 0, let's give ourselves a point with coordinates x1, x2. What we want to do is to get the length of the directed line segment from O to P. And we can use Pythagoras to do that. This directed line segment is usually denoted, by the way, by square brackets, and we use the round brackets to denote the point. Then if we project down onto the x-axis, that's the point, let's call it Q, with coordinates x1 and 0. So this is x1 here, this line here from O to Q. This has coordinates x1, and x2 goes from Q to P. So, of course, we have then a right angle triangle here, x1, x2, and the length of the line is the square root of the sum of the squares. Well, we've applied the theorem of Pythagoras to two-dimensional space. Let's have a look at what happens in three-dimensional space, R3, the set of all triples of real numbers. We want to get the distance from the origin, 0, 0, 0, now 3 coordinates, and to the point P. And let's give it coordinates x1, x2, x3. We want to get an expression for the length of the line from O to P, the directed line segment or vector from O to P. Now, again, the notation that we normally use is that round brackets denote a point, and square brackets denote the directed line segment to that point from the origin. We want an expression for the length of the line. The usual notation for it is this double bar here, So that stands for the norm of x, or the length of the vector x. And we want to get an expression for that in terms of the x1, x2, and x3. Now we've got Pythagoras' theorem in 2 space. The length of the line from 0, 0 to x1, x2 is square root of x1 squared plus x2 squared. Now what does it look like in 3 space? Can you pause the video here and do it yourselves? See what you get. Alright, you should have. Have you done that? Don't click until you've done it. Right, here it comes. You should have got this. And in the next slide, I'll show you how that was obtained. Well, this is what a proof would look like. We set up the stage. We've got a point with its 3 coordinates, and we take the projection of that point down to the x1, x2 plane, and we'll call that Q, with its 0 third coordinate. Project again onto the x2 axis, and the coordinates of the point are 0, x2, 0. Project onto the x1 axis, and that point has coordinates x1 and 0, 0. There's x1, there's x2, and here is x2 again. So we look at the length here, this length here, that's the length of a hypotenuse of a triangle, this one in the flat plane here in the x1, x2 plane, and s squared is x1 squared plus x2 squared. Let's write that down. Then we look at this triangle, this vertical triangle. There's x3, and there's the other length of this vertical triangle, and there is the hypotenuse. That's the one we're trying to find. And the length of the hypotenuse is the square root of the sum of the squares of the 2 sides, that squared plus that squared. So we use the usual notation, these double lines here, to denote the length of a vector, and it's s squared plus x3 squared. And of course, s squared we established was x1 squared plus x2 squared. And there we have it. Extending even further now, if we've got a point in n-dimensional space, and there is the origin in n-dimensional space, that's the vector from O to P in n space, then we'll define the length to be the square root of the sum of the squares of all of the components. There's a very interesting extension to Pythagoras' theorem. Let's just set up our right-angled triangle again with sides A, B, and C. And before, we proved that c squared is a squared plus b squared. And those were areas of squares erected on the corresponding sides. But the theorem also works if they're not squares, if they're semicircles. So we erect semicircles now. And if we make these definitions, capital A is going to be the area of the semicircle down here with the side A, with the diameter A. And similarly for capital B and capital C. So capital A, capital B, capital C. Now remember, the area of a circle is pi times the radius squared. So for a semicircle, it's half of that. And the radius of this one here is half A. So we can very easily compute the area here. It's a half pi radius squared, and the radius is A over 2. So it's pi over 8 times A squared. And similarly for capital B, the area here, it's pi over 8 times B squared. And similarly for this one, it's pi over 8 times C squared. So all of these areas are fixed multiples, the same multiple of the square here, of the square of the side. So what is the area here? Capital C, it's pi times c squared over 8, pi over 8 times c squared, and c squared, we know from Pythagoras' theorem before, is a squared plus b squared, and multiply out, and that is the area of A, and that is the area of B. And you can extend this even further. It doesn't have to be semicircles. You can erect figures on here, such as, say, pentagons or triangles. They must all be similar, and they must all have the fact that their areas are the same multiple of the length squared. So I'm going to give you some homework. There's our triangle set up again with its lengths A, B, and C. Now, you do this. Erect on each side a triangle. Perhaps you could make it an equilateral triangle in each case, or each triangle must be such that the ratio of the height to the length is the same. And see if then you can get the same result as we did for the semicircles. And when you finish with that, put pentagons here. So make this one side of a pentagon, and this one side of a pentagon, and the same with this one, and get the same result.